Welcome to Sleepy Stories, the place where calm and curiosity share the same quiet sky. Here, you can let your thoughts drift while you learn. These stories are designed to help you rest, but also to keep your mind gently awake in wonder. You do not need to fall asleep right away. The universe has waited billions of years, and it can wait for you too. If these nights bring you peace, we invite you to like and subscribe. Each small gesture helps us keep creating new journeys through science and stillness. Now let us turn outward, to the space that surrounds everything you know. The universe is not only a backdrop for stars, it is the total framework of existence, space, time, matter and energy woven together by consistent physical laws. When we look up at night, we see just a thin sample of this immensity. The light from a faint star may have traveled for hundreds or thousands of years before reaching your eyes. What you see is history, streaming continuously toward you. Astronomers estimate that the observable universe stretches roughly 93 billion light-years across. That phrase, observable, is essential because what we can see depends on how far light has had time to travel since the beginning. Beyond that horizon, space may continue without limit. In every direction lie billions of galaxies, each containing billions of stars. Some of those stars harbor planets. Some of those planets carry oceans. And on at least one, matter has learned to ask where it came from. The word universe has a precise meaning in physics. It includes all of space and time, all forms of energy and matter, and the laws that govern their behavior. Modern cosmology treats it as a measurable entity described by equations. Yet the same word also carries a poetic sense of unity, the turning of everything into one system. Scientists quantify it with data, while philosophers and poets use it to describe belonging. Both interpretations matter. One explains how it works, the other reminds us that we are part of it. For most of human history, the sky appeared eternal and fixed. Ancient observers mapped constellations and saw divine order in the motion of planets. It took millennia to realize that the stars are suns and that the Milky Way is only one galaxy among uncounted others. The telescope expanded perception just as language once expanded thought. Every technological step, from Galileo's lens to the James Webb Space Telescope, has pushed the edge of darkness a little farther away. Science now tells us that space itself can stretch. Distant galaxies are not racing through a pre-existing void. The fabric of space-time between them is expanding. This discovery, first quantified by Edwin Hubble in the early 20th century, transformed our understanding. It implies that the universe had a beginning, a hot, dense state that cooled and spread. From that initial moment emerged matter, radiation, and the physical constants that still define reality. What once sounded like a myth, the birth of everything from nothing, became a measurable event, supported by evidence such as the cosmic microwave background. The scale of these facts challenges the human mind. Numbers like 10 trillion or 90 billion are easy to recite, yet impossible to feel. Still, we can grasp patterns. Light travels at about 300,000 kilometers per second, and even at that speed, it needs over 8 minutes to reach us from the Sun. The nearest star beyond that, Proxima Centauri, is more than 4 light-years away. When you gaze at the night sky, you are seeing into the past, a natural time machine powered by photons. And yet, within that immensity, everything follows order. Gravity shapes the orbits of planets. Nuclear fusion powers the stars. The same chemistry that builds galaxies also forms the molecules in your body. The atoms that allow you to breathe, think, and sleep were once part of stars that lived and died long before Earth existed. You are not separate from the cosmos, but a continuation of its process, organized for a while into awareness. As you breathe in, imagine the quiet between galaxies. Each inhale draws in molecules older than the planet itself. Each exhale releases them back into the same cycle. There is no hurry in this rhythm. The universe expands at its own pace, and you can rest within that certainty. Even motionless, you are moving with it, spinning with the Earth, orbiting the Sun, drifting with the Milky Way through the expanding fabric of space-time. So tonight, let the scale of things be comforting rather than overwhelming. Infinity does not demand understanding, it invites perspective. The more we learn, the more we see that knowledge and peace come from the same source, observation without resistance. As you settle into stillness, remember that you are part of the greatest experiment ever run, the universe observing itself through consciousness, gently aware, quietly infinite. To understand the word universe is to understand the framework that holds everything together. In science, the universe is not a location but a totality, the sum of space, time, matter, energy, and the laws that govern them. Nothing exists outside it. Even the concept of outside has no meaning beyond it. Physicists describe it using mathematical models that tie geometry, energy, and motion into one continuous system. When you look upward or inward, every observation belongs to this same universal fabric. At its foundation lies space-time, a four-dimensional continuum where three spatial dimensions merge with one of time. Einstein's theory of general relativity replaced the old idea of gravity as a pulling force with the notion that matter curves space-time, and that curved geometry tells matter how to move. This relationship means that the universe is self-consistent. It shapes itself continuously through its own energy and mass. Galaxies orbit along invisible curves, planets fall through bent geometry, and even light follows these paths as it travels through the cosmic web. The observable part of the universe contains an immense variety of phenomena, yet all obey the same physical principles. The laws governing atoms in a laboratory also govern quasars billions of light-years away. This uniformity is one of cosmology's most profound insights, that order persists across incomprehensible distances. It allows scientists to describe the entire universe through a single set of equations, expressed in constants like the speed of light, the gravitational constant, and Planck's constant. Every interaction, from a falling leaf to the orbit of a galaxy, follows from these same fundamental rules. When cosmologists refer to the universe, they often mean the LCDM model, short for lambda cold dark matter. Lambda represents dark energy, the mysterious form of energy causing the universe's expansion to accelerate. Cold dark matter describes the unseen mass that provides the gravitational framework for galaxies and clusters. This model, built from precise observations, describes the universe's structure with remarkable accuracy. It tells us how matter clumped together after the Big Bang, how expansion has evolved, and how cosmic background radiation carries the imprint of those earliest moments. But even this grand model covers only what can be measured. The universe could be much larger than the observable region, possibly infinite, possibly curved back upon itself like the surface of a sphere. If it loops in on itself, traveling far enough in one direction might one day bring you back to your starting point, though the expansion of space likely makes such a journey impossible. In contrast, if space is infinite, then galaxies repeat endlessly in patterns we will never see. Both possibilities are consistent with physics, neither breaks the laws that define the whole. On smaller scales, everything within the universe is structured hierarchically. Atoms form molecules, molecules form minerals, and these combine into planets. Stars cluster into galaxies, galaxies into groups, and groups into filaments spanning millions of light-years. The universe is not chaotic but organized by predictable processes driven by gravity, thermodynamics, and quantum mechanics. Yet, within this order, complexity flourishes, a self-organizing system where matter explores its own potential forms. To see the universe this way changes how we define our place within it. The boundary between observer and observed dissolves. Your body is composed of the same elements forged in ancient stars, bound by the same forces that hold galaxies together. Understanding this does not diminish individuality. It expands identity to cosmic proportions. You are not separate from the physical laws of the universe. You are one expression of them, briefly aware and able to ask questions about the whole. In this vast continuity, even stillness holds meaning. Space itself is dynamic, constantly stretching and curving, even in what appears to be emptiness. Quantum fields flicker beneath that stillness, producing particles that appear and vanish. Gravity maintains order through this motion, ensuring that galaxies, stars, and planets follow their paths in quiet obedience to equations older than life itself. The universe is not random chaos, but patterned energy unfolding through time, a system stable enough to allow thought, fragile enough to inspire wonder. So when scientists speak of the universe, they do not describe a place you can visit. They describe everything that is, including the space between things and the time that separates moments. The term unites all experience, the light of stars, the dust of comets, and the single breath you take in this quiet moment. In that breath lives the same physics that moves galaxies. And while your eyes close and thoughts begin to slow, those same universal laws continue their work, steady and eternal, keeping the cosmos in motion and your world intact. If the universe is the total of everything, then distance becomes its most humbling measurement. Between the stars, space stretches across incomprehensible ranges. The nearest star beyond our Sun, Proxima Centauri, lies over 40 trillion kilometers away. Such numbers exceed human intuition, so astronomers use light itself as their ruler. A light year is the distance light travels in one Earth year, about 10 trillion kilometers, and it becomes the universal yardstick for cosmic scale. Every point of light you see in the sky is not a present image, but an echo of the past, because light, though fast, is not instantaneous. To measure the universe, astronomers build what is called the cosmic distance ladder, a sequence of overlapping techniques, each extending the reach of the previous. For nearby stars, they use parallax, observing how a star's position appears to shift against the background when Earth moves around the Sun. The angle of that shift reveals its distance through simple geometry. Beyond a few thousand light-years, this method fails, so scientists turn to standard candles, objects of known brightness such as Cepheid variable stars and Type Ia supernovae. By comparing their true brightness to their observed brightness, distance can be inferred with striking precision. At the farthest reaches, light itself becomes the guide. As the universe expands, the light waves from distant galaxies stretch, a phenomenon called redshift. The greater the redshift, the faster a galaxy is moving away and the farther it is from us. This connection between distance and redshift forms the foundation of modern cosmology. Observing the faintest, reddest galaxies means looking billions of years into the past, to times when the universe was young and dense. Space is not only vast, it is a timeline woven into geometry. This fusion of space and time is one of Einstein's most revolutionary insights. Distance in the cosmos cannot be separated from duration. To see far is to see long ago. When you look at a galaxy 10 billion light-years away, you see it as it was 10 billion years in the past. In that moment, the telescope becomes a time machine, capturing photons that have traveled undisturbed across expanding space since before Earth formed. The night sky is therefore both map and memory, an archive of cosmic history written in light. Even within our own galaxy, distances are astonishing. The Milky Way spans roughly 100,000 light-years, and light from its far rim takes that long to reach us. Our solar system, though immense to human eyes, is only a microscopic dot within that structure. The nearest spiral galaxy, Andromeda, lies over 2 million light-years away, and in the distant future, billions of years from now, it will merge with the Milky Way in a slow gravitational dance that will reshape both galaxies entirely. The scale of motion is so large that even cataclysm happens in silence. To comprehend such immensity, astronomers rely on units that turn abstraction into manageable form. The astronomical unit for distances within our solar system, the parsec for interstellar measures, and the megaparsec for galactic maps. Each step upward reveals patterns of motion that obey the same physical laws. The precision of these methods allows scientists to chart not just where galaxies are, but how fast the universe expands and how its structure evolves over time. And yet, even this accuracy has a boundary. The farther we look, the more expansion stretches the light until it fades beyond detection. There is a limit, the cosmic horizon, beyond which no signal can ever reach us, because space itself expands faster than light can travel. Beyond that horizon lies a region forever invisible, not because it lacks light, but because time and space forbid connection. In that sense, our universe is both endless and enclosed, a vast sphere of visibility surrounded by mystery. For the mind, such scales might feel overwhelming, yet they also offer a strange comfort. The distances between galaxies, the patience of light, the quiet accuracy of geometry, all remind us that reality is orderly, measurable, and comprehensible, even when it exceeds comprehension. As you rest, imagine that light still travels through the dark, carrying ancient stories across impossible distances, steady as breath. You are part of that journey, an observer inside the very equation that measures itself. When astronomers first turned their telescopes toward distant galaxies, they expected to find random motion, some objects moving closer, others moving away. Instead, they discovered a pattern. Nearly all galaxies were receding. In the 1920s, Edwin Hubble measured this relationship between distance and velocity and revealed something profound. The universe was not static, space itself was expanding. What seemed unchanging to human eyes was, in truth, dynamic and alive on a scale of billions of light-years. To understand expansion, imagine the surface of a balloon covered with small dots. As the balloon inflates, the dots move apart, though none of them are flying through the surface itself. Space behaves in a similar way. Galaxies are not rushing through a void, but carried apart by the stretching of the space between them. Every point sees every other point recede. There is no center, no privileged position from which expansion radiates, because space expands everywhere at once. From any galaxy's perspective, all others appear to be moving away. The rate of this expansion is expressed by the Hubble constant, measured in kilometers per second per megaparsec. Each megaparsec, about 3 million light-years, shows a proportional increase in velocity. When astronomers plot distance against redshift, the graph forms a near-perfect line, confirming the proportional relationship between space and motion. Light from receding galaxies stretches, lengthening its wavelength and shifting its color toward red. This redshift is not a Doppler effect in the usual sense. It arises because space itself expands while the light travels through it. The longer the journey, the greater the stretching. This discovery transformed cosmology. A dynamic universe implies a beginning, a moment when all of space was concentrated into an extremely hot, dense state before expansion began. That concept, now known as the Big Bang, does not describe an explosion in space but an expansion of space itself. Every region of the cosmos once overlapped. Every particle of matter and energy shared the same origin. Even now, the radiation left from that event, the cosmic microwave background, fills all directions equally, a faint afterglow of creation that proves the universe has been evolving ever since. Expansion does not occur within a pre-existing emptiness. It creates the emptiness as it grows. Galaxies are gravitationally bound islands within the rising tide of space-time. On smaller scales, within clusters and superclusters, gravity overcomes expansion, keeping systems intact. But beyond those scales, expansion dominates, pulling galaxies apart faster than their mutual gravity can resist. Over cosmic time, the distances between galaxy clusters will grow so vast that light from each will fade beyond detectability, leaving isolated islands of stars adrift in the dark. This stretching of space also stretches time. The light from a distant supernova not only shifts in color but in rhythm. Its flicker slows, its energy spreads thinner. Every observation becomes a dialogue between what was and what is now. Cosmologists use this effect to trace the universe's expansion history, comparing data from galaxies near and far to refine our understanding of how fast the cosmos grows and whether that rate changes. The evidence shows that expansion once slowed under gravity's pull, then began accelerating, a mystery still under investigation. From a human perspective, such motion is imperceptible. The Milky Way and Andromeda will not feel this expansion locally because gravity binds them together. But on the grand scale, the universe stretches silently, its geometry evolving like a slow breath of creation. The same laws that move galaxies also govern the falling of an apple. The difference is only scale and time. To rest within this knowledge is to see the universe as both vast and intimate. Expansion is not chaos, it is order unfolding, the mathematical expression of energy spreading evenly through space-time. Each second that passes is part of this universal rhythm. As you listen, your own breath expands and contracts with the same quiet regularity. The cosmos grows not with noise but with consistency, a silent movement that continues even when no one watches, a gentle assurance that everything, everywhere, is part of one continuous motion without edge or center. Every theory in science must be tested by observation, and the idea of a universe that began from a hot, dense state once seemed impossible to verify. Yet evidence arrived quietly, in the form of faint radio noise that filled the sky. In the 1960s, two engineers, Arno Penzias and Robert Wilson, were testing a large antenna when they detected a persistent hiss. It came from every direction, day and night, and no adjustment could remove it. What they had found was not interference but the oldest light in existence, the cosmic microwave background, the cooled echo of the universe's origin. This radiation is the leftover heat from the moment when matter and light first separated. In the early universe, roughly 380,000 years after the Big Bang, temperatures had cooled enough for electrons and protons to combine into neutral atoms. Light, previously trapped by constant collisions, could now travel freely. That first light still travels through space today, stretched by cosmic expansion into the microwave part of the spectrum. Every part of the sky glows faintly with this ancient signature, uniform to within 1 part in 100,000. Satellites such as COB, WMAP, and Planck have mapped this radiation in extraordinary detail. They revealed minute fluctuations, slight differences in temperature that record the earliest seeds of structure. Where the glow is slightly warmer, the universe contained marginally more matter, where cooler, slightly less. Over billions of years, gravity amplified these variations, forming galaxies, stars, and planets. The entire cosmic web grew from those first, delicate ripples in a sea of light. What we now call the observable universe is the evolved pattern of those tiny imperfections. The uniformity of the cosmic microwave background confirms that the universe was once far denser and hotter than it is today. Its blackbody spectrum matches precisely the predictions of the Big Bang model, a level of accuracy that no alternative theory has matched. This radiation's temperature, just 2.7 Kelvin above absolute zero, is a scientific relic, evidence that all matter once shared a common origin and has since cooled as space expanded. The same photons that warmed the young universe now pass invisibly through every room, through every human body, reminders of an era long before life began. From this data, scientists can reconstruct a timeline of cosmic history. The first fractions of a second after the Big Bang saw rapid inflation, when the universe expanded faster than light can travel, smoothing out irregularities. Matter and radiation filled space uniformly. As expansion continued, the universe cooled enough for particles to form, then atoms, then stars. Each stage left measurable traces, in background radiation, in the abundance of light elements, like hydrogen and helium, and in the large-scale distribution of galaxies. These clues align perfectly, forming a cohesive narrative of cosmic evolution grounded in mathematics and observation. To visualize this is to imagine light itself as a messenger. Every photon of the cosmic background has been traveling unimpeded for more than 13 billion years, carrying information about the state of the cosmos when it was still a newborn. Each microwave signal that reaches Earth's detectors is a letter from the past, written in radiation instead of ink. Together they compose a portrait of beginnings, a universe once blazing with energy, now vast and cool, yet still echoing with its first breath. There is something deeply peaceful in this knowledge. The universe does not hide its origin behind myth or mystery. It broadcasts it continuously, softly, through wavelengths that fill all of space. You are surrounded by the same light that once illuminated everything. It passes through you as you sit or lie still, tracing a silent bridge between what was and what is. The evidence of the beginning is not distant. It hums around you, gentle and patient, waiting for quiet minds to listen. The universe expands, yet it does so without sound or pulse, an ongoing stretch of space-time too slow for human senses to detect. Still, that motion has a rhythm, a measurable tempo expressed by the Hubble constant, which describes how fast galaxies drift apart. This constant is not truly constant. Refined measurements reveal subtle differences depending on the method used, sparking one of modern cosmology's great debates. But whether the rate is 67 or 74 kilometers per second per megaparsec, the meaning remains. Everything is moving, quietly, together. Scientists measure this expansion through light. As galaxies recede, their emitted wavelengths stretch, a phenomenon called cosmological redshift. Observing these stretched wavelengths allows researchers to calculate velocity and distance, building a kind of cosmic heartbeat, a steady expansion that has persisted since the first moments after the Big Bang. Each observation of redshift is a glimpse into that slow breathing of space, an invisible rhythm that underlies all motion. It is science's most silent symphony, a song without sound, yet universal in scope. This rhythm is constant and indifferent, yet it resembles something deeply human, the calm expansion and contraction of breath. When you inhale, air moves into the lungs, expanding the chest cavity. When you exhale, it releases, returning to rest. On a much larger scale, space itself stretches and releases energy in waves of motion that follow no human timing but mirror our biological patterns. The same physical principles apply in both cases: pressure, energy, and equilibrium. Where the cosmos expands outward, you expand inward with breath. If you were to visualize the galaxies as points on a vast, elastic sheet, you would see each one moving slowly away from the others, carried by the stretching of the fabric itself. That quiet motion is everywhere, even in the space between the atoms that form your body. It is not noticeable because the distances on small scales are governed by stronger forces, electromagnetic bonds that hold matter together. But on grand scales, where gravity weakens and distance dominates, expansion becomes the rule, a long exhale of creation. As the universe grows, it also cools. The same principle that lets your body release heat during rest applies to the cosmos as a whole. Energy spreads evenly, temperature drops, and equilibrium increases. The night sky, filled with stars, seems unchanging, but every second the background radiation stretches and thins. This gradual cooling defines cosmic time itself. Each breath you take aligns, unknowingly, with the same physics: pressure balancing expansion, temperature finding equilibrium, motion slowing toward calm. In this vast comparison lies a profound comfort. The universe does not rush, and it does not pause. It continues to expand with steady patience, a persistence free from urgency. In that steadiness, the mind can find a reflection of peace. There is no need to match the cosmos in scale. It is enough to match its tempo. Let each inhale rise like the forming of galaxies. Let each exhale drift like light traveling through deep space, constant, effortless, infinite in direction. Even the instruments that measure cosmic expansion, radio arrays, optical telescopes, gravitational detectors, must wait for light to arrive. Every observation is an act of patience, collecting photons that began their journey billions of years ago. In a sense, astronomers practice the same stillness they study, watching without interference, allowing signals to reach them naturally. The science of the universe is not built on chasing but on waiting, listening to what reality reveals when given time. So as you rest, imagine that your breath is synchronized with that silent expansion. Each exhale widens the universe by a fraction of a fraction of a fraction of space. You are not separate from this rhythm, you are one expression of it. The cosmos expands whether you are awake or asleep, and that continuity is peace itself, motion without effort, creation without noise. In stillness, you follow the same law that governs galaxies: to move, not through force, but through the natural unfolding of space and time. When you picture the universe, you might imagine an infinite void or a vast sphere filled with stars. Yet cosmology asks a subtler question: what is the shape of all space itself? Geometry does not belong only to classrooms and diagrams. It defines the structure of reality. In Einstein's general relativity, matter and energy bend space-time, creating curvature. That curvature, in turn, determines how objects move, how light travels, and ultimately, the fate of the universe. To describe this curvature, scientists consider three broad possibilities: closed, flat, or open. A closed universe curves back on itself like the surface of a sphere. Travel far enough in one direction and, in theory, you could return to your starting point. Such a cosmos would be finite yet unbounded, with no edge. An open universe has negative curvature, like a saddle, expanding forever but thinning with time. Between these extremes lies the flat model, space that extends without bending, balanced precisely between collapse and endless expansion. Determining which geometry describes our universe required decades of observation. Cosmologists turned to the cosmic microwave background, that ancient afterglow from the Big Bang, as a natural map of space. If the universe were curved, the light from those earliest moments would trace arcs and distortions across the sky. By measuring the angular size of fluctuations within that radiation, satellites like Planck and WMAP revealed the result. Space is remarkably flat, with curvature so close to zero that any deviation is smaller than our instruments can detect. A flat universe does not mean two-dimensional or featureless. It means that parallel lines, if extended forever, never meet or diverge. Triangles drawn across cosmic scales add up to 180 degrees, just as they do on a sheet of paper. This geometric simplicity allows cosmologists to make precise calculations about the age, size, and fate of the universe. A flat geometry aligns neatly with inflation theory, the idea that the early universe underwent a period of rapid exponential expansion that smoothed out any initial curvature, leaving behind a balanced, uniform cosmos. The implications of flatness reach beyond mathematics. If the universe is perfectly balanced between gravity's inward pull and expansion's outward drive, then its large-scale behavior reflects equilibrium on the grandest scale imaginable. Gravity tries to fold space inward, expansion stretches it outward, and the result is a near-perfect standoff. This balance mirrors countless smaller systems in nature: the orbit of planets, the oscillation of atoms, even the regulation of biological life. Everywhere, stability emerges from tension between opposing forces. Despite this global flatness, local curvature remains. Stars bend the space around them, planets carve small dimples into space-time, and black holes create extreme wells where even light cannot escape. The cosmic fabric, therefore, is not smooth like glass but subtly textured, its geometry shaped by matter at every scale. When astronomers observe light from distant galaxies curving around invisible mass, forming arcs and rings, they witness gravity revealing the shape of space directly. It is geometry written in light. For the human mind, these abstractions invite reflection. To live within a flat, expanding universe is to exist in perfect geometric neutrality, balanced yet dynamic. Space bends gently where mass gathers, but overall it stretches evenly, a calm sea of mathematics expressed through stars and voids. This quiet balance carries a kind of serenity. It tells us that the cosmos, vast as it is, follows principles of elegance rather than chaos. As you settle into rest, imagine yourself floating on this geometric ocean. Every direction extends forever. Every angle aligns in harmony. You are weightless, suspended in a flat expanse that neither collapses nor drifts apart. The same laws that define cosmic curvature hold you in equilibrium, moment by moment. The shape of space may be infinite, but its balance is immediate, surrounding you in invisible precision, a universe perfectly shaped for peace. Gravity is the oldest force we know. Long before people could describe it mathematically, they watched apples fall and moons circle planets, sensing an invisible pull binding the heavens to the earth. For centuries, gravity was imagined as attraction, a mysterious influence acting across empty space. Then came a revolution. In the early 20th century, Albert Einstein redefined gravity not as a force but as a property of geometry itself. According to his general theory of relativity, mass and energy curve the fabric of space-time, and that curvature tells matter how to move. Picture space-time as a flexible sheet. When you place a heavy object on it, the sheet dips. Smaller objects move toward that dip, not because they are pulled by an unseen string, but because the sheet guides their motion along curved paths. This is how the planets orbit the sun, not by being pulled, but by following the contours of space-time, sculpted by solar mass. Even light, though massless, bends when it passes near massive objects, tracing the shape of gravity's invisible architecture. This bending of light, called gravitational lensing, allows astronomers to see galaxies otherwise hidden behind others. The light from a distant source arcs around a massive cluster, producing mirrored or ring-shaped images. These natural lenses serve as cosmic magnifying glasses, revealing details of galaxies billions of light-years away. By studying the degree of bending, scientists can also measure mass that emits no light at all, evidence for dark matter's pervasive influence. In this way, gravity becomes both a sculptor and a messenger, shaping the cosmos and allowing us to read its design. General relativity also predicted something subtler: gravitational waves, ripples in the fabric of space-time produced by accelerating masses. For a century, they remained theoretical, too faint to detect. Then, in 2015, Instruments of the Laser Interferometer Gravitational Wave Observatory recorded the signal of two black holes merging over 1 billion light-years away. The detection confirmed Einstein's prediction and opened a new window on the universe. Since then, dozens of such events have been recorded, each one a tiny vibration in the geometry of existence itself. These waves stretch and compress space by incredibly small amounts, smaller than a proton's width. Yet their detection proves that the cosmos is dynamic all the way down to its structure. Space-time is not a static stage, but an active participant, a medium that vibrates, bends, and evolves. Every orbit, collision, and movement of mass leaves an imprint on this invisible fabric. The universe, at its most fundamental level, is alive with motion, even in silence. To grasp this idea is to see unity where separation once seemed absolute. Matter tells space how to curve, and space tells matter how to move. Neither can exist independently. Without mass, space-time would have no shape. Without space-time, mass would have nowhere to be. It is a perfect reciprocity, an unending conversation between geometry and substance, rhythm and rest. For a moment, let that image replace the idea of emptiness. Imagine that everything around you, the chair, the air, your own body, is part of a single, flexible medium, curving slightly under its own weight, connected seamlessly to distant galaxies. Every movement, however small, creates a ripple that merges into the greater whole. Just as a planet travels through the warp of space, a thought moves through the geometry of the brain, following its own pattern of energy and rest. The same principles apply, scaled by gravity and time. As you breathe, feel how even stillness participates in this universal dance. Gravity anchors you gently to the Earth, while the Earth itself curves space around the Sun. Far beyond, galaxies trace invisible spirals through the bending of cosmic fabric. Everything moves in harmony with geometry, silently and precisely. The pull you feel is not confinement, it is connection. Gravity holds the universe together so that life, thought, and sleep can unfold in peace within its embrace. If you could gather all the matter in the universe and sort it by kind, the result would surprise you. Everything visible, stars, planets, gas, dust, oceans, and living beings, makes up less than 5% of the cosmic total. The rest is invisible, detectable only through its effects. About 27% is dark matter, unseen but massive, shaping galaxies with its gravity. The remaining 68% is dark energy, a mysterious form of energy that drives the universe's accelerating expansion. We live in a cosmos where what we cannot see vastly outweighs what we can. Ordinary matter, called baryonic matter, is built from protons, neutrons, and electrons, the familiar ingredients of atoms. These atoms assemble into hydrogen and helium, the lightest elements formed during the universe's first few minutes. Over billions of years, nuclear fusion inside stars created heavier elements, later scattered by supernovae to seed new worlds. This visible matter radiates, absorbs, and reflects light, allowing telescopes to map its structure. Yet despite its brilliance, it is only a thin trace in the larger balance of energy and mass. Dark matter reveals itself through gravitational influence. In the 1930s, astronomers noticed that galaxies within clusters moved too quickly to be held together by visible mass alone. Later, Vera Rubin's studies of spiral galaxies showed that their outer stars orbited faster than expected, as if surrounded by an unseen halo of mass. This invisible material does not emit or absorb light, it interacts only through gravity and perhaps through unknown weak forces. Modern observations of cosmic microwave background patterns, gravitational lensing, and large-scale structure all confirm its presence. It forms the scaffolding of the cosmos, providing the gravitational framework within which galaxies take shape. Yet dark matter explains only part of the mystery. In the late 20th century, astronomers measuring distant supernovae discovered that the universe's expansion was accelerating. Gravity, which should slow expansion, was losing the contest. To account for this acceleration, scientists proposed dark energy, a smooth, uniform energy field filling space itself. Its effect is repulsive, counteracting gravity on the largest scales. Whether it is a constant property of space, as Einstein once proposed, or something dynamic that evolves with time remains one of cosmology's most profound questions. These discoveries transformed the picture of the universe from matter-dominated to energy-dominated. The LCDM model, combining dark energy lambda and cold dark matter, successfully predicts the observed distribution of galaxies, the geometry of space, and the age of the cosmos. Though we cannot yet explain what dark energy or dark matter truly are, their existence is undeniable. They shape every star and determine the universe's destiny, operating silently beyond sight, the way deep ocean currents shape the motion of waves. It is humbling to realize that all human history, every life, every invention, every word, unfolds within that tiny, luminous fraction of reality. The atoms of our bodies belong to the same category as stars, yet we are surrounded by an invisible ocean of unknown energy and mass. The night sky glows faintly with the visible portion of creation, while the rest remains transparent, detectable only through mathematics and gravitational traces. We are children of light living in a mostly dark universe. And still, that darkness is not emptiness. It is structure waiting to be understood, order beyond perception. Physicists continue to search for new particles in underground laboratories, to measure cosmic microwave fluctuations, and to refine theories of quantum fields. Each experiment narrows the possibilities, and with each discovery, we come closer to knowing what fills the cosmic ledger. The search itself mirrors the act of consciousness, reaching into mystery, guided by faint signals, patient enough to learn from silence. So when you gaze upward and feel the pull of stars, remember that most of the universe is unseen but not unknowable. The laws that describe it apply to every atom you contain. You are made of the visible 5%, yet your existence depends on the invisible 95%. Darkness is not absence but foundation. Within it, galaxies find form, and within you, awareness finds meaning. The night sky looks luminous, yet its brilliance hides an unseen architect. Every star, nebula, and galaxy sits within a massive, invisible halo made of dark matter, a substance that neither emits nor reflects light, yet outweighs all visible matter combined. Without it, galaxies could not hold their shape, stars would drift apart, and cosmic structure would dissolve. Dark matter is the universe's hidden skeleton, shaping everything we see while remaining entirely undetectable to the eye. Astronomers first suspected its existence when they noticed that galaxies rotated too quickly. According to Newtonian mechanics, stars at the outer edges should orbit more slowly than those near the center, where most of the mass lies. Instead, they moved at nearly constant speeds, as if enclosed within a vast sphere of unseen mass. These rotation curves, confirmed by Vera Rubin's meticulous work, provided direct evidence that most of a galaxy's mass is invisible. Later, gravitational lensing, where light from distant objects bends around massive clusters, revealed similar results. The bending was too strong to be explained by visible matter alone. The hidden mass was everywhere, holding the cosmos together. Today, dark matter explains the large-scale pattern of the universe. Simulations of cosmic evolution show that without it, galaxies would never have formed. Its gravity provided the framework into which normal matter fell, cooling into stars and planets. The cosmic web, an intricate lattice of filaments and voids, traces dark matter's invisible contours. Even the temperature variations in the cosmic microwave background carry its imprint, showing how it guided structure formation from the earliest moments. Every known observation fits this unseen architecture with uncanny precision. Yet, despite its gravitational fingerprints, no one has seen a single dark matter particle. Scientists propose several candidates. The most widely studied are WIMPs, weakly interacting massive particles. These hypothetical particles would interact through gravity and the weak nuclear force, but not with light. Deep underground, detectors cooled to near absolute zero wait for rare collisions between WIMPs and atomic nuclei. So far, none have been confirmed. Another possibility is the axion, an ultralight particle that could behave more like a field than a particle, subtly influencing electromagnetic radiation. Experiments using resonant cavities and quantum sensors continue to search for its faint signal. There are other ideas too: sterile neutrinos, supersymmetric particles, even modifications of gravity itself. Each theory extends physics beyond the standard model, testing the limits of what we know. The absence of detection does not weaken belief in dark matter. It strengthens the mystery. The evidence for its gravitational effect is overwhelming, but its nature remains one of the universe's most elegant puzzles, a riddle written in equations and curves of starlight. For scientists, this pursuit carries philosophical weight. To study something invisible requires faith in evidence, patience, and humility before the unknown. The dark matter problem reminds us that most of existence lies beyond direct perception. We are creatures of light, yet we live inside shadow. The visible world, comforting in its clarity, floats atop an ocean of hidden mass that shapes its destiny. What we call empty space is, in truth, dense with potential, fields and particles waiting to be understood. There is a certain calm in that realization. Mystery is not a flaw in knowledge, it is its foundation. The cosmos continues to expand and evolve, whether or not we have named all its components. The search for dark matter is, in essence, the search for the rest of reality. It mirrors our own curiosity, our desire to look deeper than appearances. Even in darkness, the universe follows rules, laws that hold true from the smallest atom to the farthest galaxy. As you let your thoughts settle, imagine this hidden mass surrounding you, silent but constant. It passes through your body, through the earth, through every star. Trillions of dark matter particles may drift through you each second without leaving a trace, like invisible rain. You exist within that gentle flow, carried by forces unseen but entirely real. The universe does not need to be visible to be known. Sometimes, the greatest truths are the ones that hold everything together quietly. In the late 20th century, astronomers expected to confirm that the universe's expansion was slowing down. Gravity, after all, should act as a universal brake, tugging on galaxies and drawing them gradually inward. Instead, the data told another story. Observations of distant Type Ia supernovae, used as reliable standard candles, revealed that these stellar explosions were dimmer than predicted, farther away than expected. The conclusion was astonishing. The universe's expansion was not slowing, but speeding up. Something unseen was pushing galaxies apart with increasing force. That mysterious agent became known as dark energy. Dark energy now dominates the cosmic budget, comprising about 2/3 of all energy in the universe. Unlike dark matter, which clumps and pulls, dark energy acts evenly everywhere, as if space itself possessed an inherent pressure that drives expansion. One possible explanation is that dark energy corresponds to the cosmological constant, a term Einstein once inserted into his equations to maintain a static universe. When expansion was later discovered, he called it his greatest blunder. Yet the constant he abandoned reappeared decades later as the simplest way to describe cosmic acceleration. What was once a mathematical correction became a window into one of nature's deepest mysteries. In general relativity, space and time respond to energy and pressure. If a uniform energy fills space, it exerts a repulsive effect on cosmic scales, causing expansion to accelerate. This concept fits the observations beautifully, but its nature remains elusive. Quantum field theory predicts that even empty space should contain energy from virtual particles appearing and vanishing. However, calculations yield values vastly greater than what is observed, a mismatch so enormous it has been called the worst prediction in physics. Somewhere between quantum mechanics and cosmology lies an answer still out of reach. Astronomers test dark energy's influence through several methods: the large-scale distribution of galaxies, subtle patterns in the cosmic microwave background, and baryon acoustic oscillations, which act as cosmic rulers measuring how structure grows. All indicate the same trend: expansion, accelerating steadily over billions of years. The universe, it seems, will continue to stretch forever unless dark energy changes over time. Some theories propose it is not constant but dynamic, perhaps a field called quintessence that evolves with cosmic age. Others suggest modifications to gravity itself might explain the phenomenon. For now, the evidence points strongly toward an unchanging, invisible pressure that fills the cosmos completely. If dark energy remains constant, the universe's future is one of quiet acceleration. Galaxies will drift farther apart until their light fades beyond our cosmic horizon. Over immense spans of time, only the closest galaxies bound by gravity will remain visible. The night sky, once vibrant with billions of stars, will gradually empty. Yet this fate is not tragic. It is simply the natural outcome of the same laws that allowed the universe to exist in the first place. Expansion is balance expressed through geometry, the continuation of what began at the first moment of creation. The discovery of dark energy reshaped more than physics. It transformed our sense of place. We live in a cosmos governed not by light alone, but by invisible principles of structure and motion. The emptiness between galaxies is not truly empty. It possesses properties, energy, and influence. Even space that seems void participates in the grand design. When you consider this, the distinction between full and empty, presence and absence, becomes less meaningful. The universe is whole, and its unseen elements are as vital as its visible ones. In the stillness of the night, you can imagine this vast expansion continuing quietly around you. Every second, space itself grows slightly larger, carrying galaxies farther apart. The same mathematics that governs that motion governs the atoms within your body. You are expanding, too, in your own way, cells renewing, thoughts widening, awareness deepening. The energy that pushes galaxies apart also pushes understanding forward. The universe accelerates not into chaos, but into ever greater openness. Every pulse of the cosmos is slow beyond imagination. Galaxies drift apart at a rate no human will ever see change, yet the motion never stops. To describe this quiet movement, scientists often speak of the universe as if it breathes, expanding and cooling, possibly one day contracting again. It is not a literal breath, but the rhythm of physics itself: density, pressure, temperature, and time shifting in a coordinated dance that spans all of existence. In the simplest cosmological models, expansion continues forever, space stretching until galaxies fade into isolation. Yet there are other possibilities. Some theories suggest that gravity, if strong enough, could one day overcome dark energy, slowing expansion and drawing everything back together in a big crunch. Others propose a cyclic model, where each collapse triggers another birth, producing a new universe from the remains of the last. A few more exotic ideas imagine a bounce in which contraction and expansion alternate endlessly, like a cosmic heartbeat. Whether eternal or cyclic, the theme is the same: motion balanced by return, creation balanced by rest. To describe these processes, cosmologists measure how the universe's expansion rate changes with time, using parameters such as the scale factor and the Hubble parameter. Observations of distant galaxies and background radiation reveal that expansion once slowed under gravity's pull before dark energy began to dominate, causing acceleration. The early universe's hot, dense state expanded rapidly, then cooled. Hydrogen and helium formed, stars ignited, and galaxies emerged. Over billions of years, this expansion became gentle, almost imperceptible, yet measurable through the light that travels to us from deep space. When you inhale, your lungs fill with air molecules that have traveled through this same expanding universe. When you exhale, they return to equilibrium, dispersing into the air that connects you to every other living being. The parallel is elegant. Just as your body expands and contracts with breath, the universe expands and evolves with energy. Both follow patterns of balance, input and release, tension and calm, activity and rest. The body's rhythm of breathing mirrors the larger rhythm of space-time itself. Scientists sometimes imagine tracing the universe's entire history as a single curve on a graph: expansion, speed, rising, falling, and perhaps rising again. The smoothness of that line conceals profound forces. Each moment of equilibrium in that curve allowed complexity to emerge, atoms to combine, stars to form, and consciousness to arise. Breathing works the same way. Stillness between inhales and exhales gives the body time to absorb, to rest, and to continue. Both rhythms depend on pauses as much as on motion. Understanding this connection brings the cosmos closer to the self. You are not separate from the physical processes that govern space-time. Your breathing, heartbeat, and even neural signals operate according to the same conservation laws that control galaxies. The carbon dioxide you exhale tonight contains atoms forged in ancient stars. Each slow breath is both personal and cosmic, an act of chemistry written into the laws of physics. As you settle deeper into rest, picture the expansion of space not as something distant, but as an extension of your own calm. The universe grows because energy seeks balance. You sleep because your body does the same. The cosmos expands evenly across billions of light years. Your lungs expand evenly with each gentle inhale. Both are forms of equilibrium, the universe maintaining itself through time, and you maintaining yourself through rest. Let each breath lengthen now, slow and effortless. Imagine galaxies drifting apart in harmony with your exhale, light stretching through darkness like a thread unbroken since the dawn of time. There is no rush in the universe's rhythm, no struggle in its balance. The same physics that carries galaxies into the distance carries you towards stillness. In that shared motion lies peace, a body breathing, a cosmos expanding, both obeying the same unhurried law. Every event in the universe happens within time, but time itself flows only one way. A glass can fall and shatter, but the fragments never leap back together. Stars burn their fuel and fade, yet no process rewinds their light into youth. This one-way motion is so familiar that we rarely question it, but physics gives it a precise name: entropy, the measure of disorder, or the number of ways energy can be arranged. The universe moves from order to disorder, from concentrated energy to diffusion, from low entropy to high. This universal trend defines the arrow of time. The second law of thermodynamics states that in any closed system, entropy tends to increase. Energy spreads out, heat flows from hot to cold, systems evolve toward equilibrium. The early universe, immediately after the Big Bang, was extraordinarily low in entropy, smooth, dense, and uniform. As it expanded, tiny variations grew into galaxies, stars, and planets. Paradoxically, Complexity and structure emerged because overall entropy increased. Local order can exist only when energy flows from one state to another, like a candle burning or the sun radiating heat into space. Life itself depends on this imbalance. We exist in the gradient between high and low energy, between heat and cold, between order and dispersal. Entropy gives time its direction. The laws of physics are mostly reversible. An equation describing a planet's orbit or a photon's motion works the same forward or backward, but entropy breaks that symmetry. A star can collapse into a black hole, but the reverse cannot happen naturally. The universe cools, expands, and disperses, and that progression defines before and after. The forward flow of time is not imposed from outside. It emerges from the statistics of countless particles seeking equilibrium. To picture this, imagine ink swirling into water. At first, the color forms intricate patterns, then gradually blends until uniform. That final state has far more possible microscopic arrangements than the initial pattern, so entropy is higher. The same principle governs galaxies and thought alike. Memory exists because physical processes in the brain record traces of the past, another expression of entropy increase. Forgetting is natural. Remembering takes energy. Even consciousness flows along the same current as the universe, a sequence of organized patterns dissolving slowly into equilibrium. Cosmologists believe that as the universe ages, entropy will continue to rise. Stars will exhaust their fuel, matter will decay, and black holes will slowly evaporate through Hawking radiation, releasing their energy back into the void. Far in the future, when all processes that generate heat have ended, the cosmos will approach a state of maximum entropy, uniform temperature, no gradients, no motion capable of doing work. This theoretical state is known as heat death, not a sudden event but a gradual fading, where time itself loses meaning because nothing changes enough to mark its passage. Yet this future should not inspire sadness. Entropy is not destruction but transformation. It is the reason stars shine and rivers flow, why hearts beat and thoughts form. Without it, the universe would be static and lifeless. Every act of creation borrows energy from a greater drift toward balance. The end of order is also the continuation of process, the universe finding stability in stillness. In that sense, entropy is not the enemy of life, but its hidden companion, the background movement that allows everything to exist for a while. As you rest, you may notice a similar rhythm in your body. Each heartbeat dissipates energy, each breath releases warmth, each thought consumes fuel. You are an open system exchanging energy with your surroundings, rising and falling with the same law that governs galaxies. When you sleep, your metabolism slows. Entropy in your body momentarily decreases locally, while the world around you absorbs the difference. Even in rest, balance continues. The arrow of time carries everything forward, gently, inevitably, peacefully, toward equilibrium. Every light in the night sky is a story in progress, a sphere of plasma sustained by a delicate balance between gravity pulling inward and nuclear fusion pushing outward. This equilibrium defines the life of a star, a process governed not by chance but by mass. From the smallest red dwarfs to the most massive blue giants, every star follows the same fundamental sequence: birth, radiance, decline, and transformation. Through this cycle, the universe renews itself continuously, turning matter into light and light back into matter. Stars begin in clouds of gas and dust called nebulae, where gravity draws particles together. As the cloud contracts, pressure and temperature rise at its core until hydrogen atoms begin to fuse into helium. This process releases enormous energy, the source of starlight. The newborn star stabilizes, entering what astronomers call the main sequence, a long period of steady fusion that can last billions of years. During this phase, The outward pressure from radiation perfectly balances the inward pull of gravity. It is a state of dynamic peace, an equilibrium that mirrors many natural systems, balance maintained through constant motion. As hydrogen in the core is consumed, the equilibrium begins to shift. Gravity gains the upper hand, compressing the star until new fusion reactions ignite. The outcome depends on mass. Smaller stars, like our Sun, expand into red giants, their outer layers swelling as the core contracts and heats. Eventually, the outer shells drift away into space, forming delicate clouds called planetary nebulae, while the remaining core cools into a white dwarf, an object no larger than Earth but with the mass of the Sun, glowing faintly for trillions of years. Massive stars follow a more violent path. Their immense gravity drives fusion through heavier elements: carbon, oxygen, silicon, and finally iron. Fusion of iron consumes energy rather than releasing it, halting the process. When the internal pressure can no longer counter gravity, the star collapses inward, triggering a supernova explosion. In that brief, blinding moment, the star releases more energy than the Sun will emit in its entire lifetime. The shock waves forge new elements: gold, silver, uranium, scattering them into space. What remains collapses into a neutron star, an ultra-dense object where a teaspoon of matter weighs billions of tons, or, if massive enough, a black hole, a region where gravity becomes absolute. This cycle of stellar birth and death forms the foundation of cosmic evolution. Every atom of oxygen in your lungs, every calcium atom in your bones, was created in the core of an ancient star that lived and died long before Earth existed. The phrase, "we are stardust," is not metaphor but chemistry. The heavy elements that make planets, oceans, and life were all synthesized in stellar furnaces and distributed across galaxies by explosions so vast that their light travels for millions of years. Out of destruction came creation, the universe recycling its own material endlessly. Stars also serve as the universe's timekeepers. Their masses determine their lifespans. Small stars burn slowly and live long, while giants blaze briefly and die young. By observing clusters of stars and comparing brightness, astronomers can estimate their ages and, by extension, the age of the universe itself. The cosmos keeps time through fusion, marking its history in cycles of light and decay. Even when a star fades, its energy persists in radiation, dust, and the atoms that find new homes in future systems. As you think of the stars above, remember that their fates are not tragic but natural. Collapse and renewal, heat and cooling, order and dispersal, these are the universe's most consistent rhythms. The death of a star is the birth of potential. The quiet ember of a white dwarf is the promise of new worlds forming from its remains. Like breath, like heartbeat, it is a pattern that never ends. To rest beneath the stars is to rest within that same cycle, to know that even in stillness, you are part of the cosmos renewing itself. Among all cosmic phenomena, none challenge understanding more deeply than the black hole. It is not an object in the ordinary sense, but a region of space where gravity becomes so strong that nothing, not even light, can escape. A black hole forms when a massive star collapses under its own weight at the end of its life. If the core's mass exceeds a critical limit, gravity crushes matter beyond atomic and even subatomic scales, creating a singularity, a point where density and curvature become infinite, and the known laws of physics cease to apply. Surrounding this singularity lies the event horizon, the ultimate boundary. It marks the distance from the center where the escape velocity equals the speed of light. Beyond that horizon, information and matter can only move inward. To an outside observer, time appears to slow as something approaches the event horizon, light stretching and fading toward red until it disappears completely. The falling object never seems to cross the boundary. It simply fades from view, leaving behind silence and shadow. This is not illusion but the geometry of space-time itself, distorted by gravity into shapes that defy intuition. Black holes come in several sizes. Stellar black holes contain a few times the Sun's mass, formed from dying stars. Supermassive black holes, millions or billions of times more massive, anchor the centers of galaxies, including our own Milky Way. There are also intermediate and possibly primordial varieties, their origins still uncertain. Despite their invisibility, black holes reveal themselves through their influence. Stars orbiting unseen centers, gas heated to extreme temperatures as it spirals inward, and gravitational waves emitted when two black holes merge. Each detection tells a story written in gravity rather than light. In the 1970s, physicist Stephen Hawking added a surprising twist. By combining general relativity with quantum theory, he predicted that black holes are not entirely black. They emit faint radiation due to quantum effects near the event horizon. This Hawking radiation arises because empty space is not truly empty. Quantum fluctuations continuously create pairs of particles and antiparticles. Near a black hole, one can fall in while the other escapes, reducing the black hole's mass slightly. Over vast timescales, this process could cause black holes to evaporate completely, returning their energy to space. Thus, even the most extreme structures in the universe participate in the same thermodynamic balance that governs everything else. The concept of information within black holes leads to one of modern physics' deepest puzzles, the information paradox. If matter and energy carry information about their state, what happens to that information when it crosses the event horizon? Quantum mechanics insists it cannot be destroyed, yet classical relativity allows no return. This apparent contradiction continues to drive research, hinting that a more complete theory, perhaps one uniting gravity and quantum mechanics, remains to be found. In this way, black holes are both mysteries and teachers, exposing the limits of our knowledge and guiding the search for new understanding. There is a profound beauty in their existence. A black hole is not merely destruction. It is a region where the universe folds inward on itself, conserving the past within invisible order. Its gravity anchors galaxies, powers quasars, and sculpts the motion of stars. It represents both an end and a beginning, a boundary between what can be known and what lies beyond observation. To study black holes is to study the frontier of reality itself. As you rest, imagine standing at that threshold, the edge of an event horizon where time slows to stillness. Beyond it lies silence, yet even there, physics continues its work with perfect precision. The same laws that govern your heartbeat govern the curvature of space. You do not need to fall into the darkness to understand it. It is enough to know that gravity, at its most extreme, is still part of the same order that keeps the universe intact. In that symmetry between the vast and the small, there is peace, an endless motion turning quietly toward balance. Between the stars stretches a vastness so deep it appears empty. Yet even the quietest reaches of interstellar space are not truly void. On average, a cubic meter of this space contains about one atom, usually hydrogen, sometimes helium. That is nearly nothing compared to the dense air around you, yet it means the universe is never completely empty. Radiation, magnetic fields, cosmic rays, and drifting particles weave through this openness like faint threads of matter and energy. To the ear, space is silent, but to a radio telescope, it hums softly with ancient signals that never stop traveling. The vacuum of space is one of nature's great paradoxes, emptiness filled with structure. It carries the faint afterglow of the Big Bang, the cosmic microwave background, bathing everything in a temperature just a few degrees above absolute zero. It holds traces of hydrogen clouds that may collapse one day to form new stars. Quantum physics tells us that even a perfect vacuum is alive with fluctuations, tiny bursts of energy appearing and vanishing constantly, giving rise to what scientists call zero-point energy. Stillness, in physics, is never absolute. Beneath the surface of silence, motion endures invisibly. In that way, the void mirrors the resting mind. When you lie in darkness and quiet, it may seem that nothing happens. Yet within, subtle patterns continue: breathing, circulation, the slow exchange of ions in your neurons. Stillness is not the absence of activity, it is activity in balance. The emptiness of space and the calm of consciousness share this quality: motion without disturbance. To enter rest is to align with the quiet rhythm that governs both body and cosmos. Astronomers have learned to read the silence of space. Instruments like radio telescopes detect faint emissions from neutral hydrogen at a wavelength of 21 centimeters, mapping the structure of galaxies and interstellar clouds. Others listen for pulsars, rotating neutron stars whose magnetic fields sweep radio beams across Earth like lighthouses. Even in apparent voids, there are whispers of structure, patterns too subtle for eyes but not for mathematics. The emptiness between stars becomes a vast archive of information, waiting patiently to be decoded. Space is also a sanctuary of equilibrium. Without air to carry sound, there is no noise, no friction, no interruption. In that stillness, particles drift for eons, undisturbed. Photons travel straight until they encounter matter. Atoms remain isolated until gravity brings them together. It is a place where time stretches almost endlessly, where energy spreads evenly, and where events unfold with infinite patience. The silence of the void is not lifeless, it is balance achieved on the grandest scale. In the same way, rest allows your body to find balance. Each breath you take releases stored energy, cooling and equalizing the system that keeps you alive. As muscles soften and thoughts slow, your internal motion continues quietly, like the faint hum of cosmic background radiation. You do not stop, you stabilize. Every cell finds its equilibrium, just as galaxies maintain theirs through gravity and expansion. Stillness, at every scale, is the universe remembering how to conserve energy. Imagine now that you are floating within this cosmic quiet. Around you stretches a darkness so vast that stars appear as fine dust. There is no wind, no sound, only the steady rhythm of your breath. The same physics that governs interstellar calm governs your body's rest. Silence is not nothingness. It is the baseline from which everything meaningful arises. In that silence, the universe expands, galaxies form, and life emerges. And in your own silence, thoughts settle, energy renews, and awareness finds its balance once more. As you drift towards sleep, you move closer to that equilibrium. The void is not an absence to fear, but a space that allows form to exist. Between every star lies the potential for creation. Between every breath lies the potential for peace. The universe breathes slowly, and so can you. Each exhale a soft echo of cosmic stillness, each pause a meeting point between matter, energy, and the endless calm that holds them. Every galaxy is a living archive of cosmic history. Each contains hundreds of billions of stars, yet none remain unchanged. Over billions of years, galaxies grow, collide, and reshape themselves in a continual process of evolution driven by gravity and time. To look at a spiral galaxy through a telescope is to see not a static object, but a vast ecosystem, stars being born in glowing clouds, old suns fading into silence, gas swirling into new formations, and invisible dark matter providing the scaffolding that holds everything together. Galaxies began as small clumps of matter in the young universe. Tiny density fluctuations in the cosmic microwave background acted as seeds where gravity could take hold. As the universe expanded and cooled, these regions gathered hydrogen and helium gas, forming the first generation of stars. Some early galaxies were irregular and chaotic, others formed simple disks. Over cosmic time, they merged into larger structures, their shapes sculpted by collisions. What emerged from this slow dance were the grand spirals, elongated ellipticals, and peculiar hybrids we observe today. In spiral galaxies, like the Milky Way, gas and dust gather in flat rotating disks, giving rise to graceful arms rich with newborn stars. Massive stars within these regions live short, bright lives, exploding as supernovae that enrich the surrounding gas with heavy elements. This material becomes the building block for new generations of stars and planets. Elliptical galaxies, by contrast, are older systems, vast, smooth collections of ancient stars with little gas left for new formation. They are often the result of mergers, their graceful shapes the aftermath of gravitational blending. Galactic collisions, though cataclysmic in scale, unfold in slow motion. When two galaxies approach, their stars rarely collide directly. The distances between stars are too immense. Instead, gravity reshapes their orbits, stretching tidal tails of gas and stars across space. Eventually, they settle into a new equilibrium, often forming a single, larger galaxy. Our own Milky Way is destined for such a meeting with the Andromeda Galaxy billions of years from now. When they merge, their central black holes will spiral together, radiating gravitational waves across the universe, a quiet finale to a long cosmic courtship. At the centers of most galaxies lurk supermassive black holes, their gravitational fields orchestrating much of the surrounding activity. When gas and dust fall toward these central regions, they form accretion disks, heating to millions of degrees and emitting intense radiation. The result can be a quasar, a brilliant beacon visible across billions of light years. These active galaxies dominated the early universe, shaping their environments through winds and jets that regulate star formation. Over time, as fuel runs out, they quiet, leaving behind dormant black holes like the one at the center of our own galaxy, Sagittarius A*. Galactic evolution also reflects the influence of dark matter. Simulations show that galaxies form along the filaments of the cosmic web, where dark matter's gravity gathers ordinary matter. This invisible structure determines not only where galaxies form, but how they cluster, spin, and grow. Without dark matter, galaxies would drift apart before stars could form. It is the hidden architecture of creation, a silent designer ensuring that light finds shape within darkness. Understanding galactic evolution is like tracing the life story of the universe itself. Each galaxy ages, transforms, and contributes to the larger cycle of matter and energy. Dust from dying stars forms new clouds, collisions spark fresh waves of star birth, black holes recycle mass into radiation. In every phase, the same fundamental laws apply: gravity, thermodynamics, and motion, each working together with quiet precision. When you gaze into the night sky, remember that the light reaching your eyes has traveled for millions of years from galaxies already transformed. Their shapes may have changed entirely by now, yet their photons continue their journey, bridging the present with the ancient. The universe, in its slow and ceaseless evolution, teaches patience. Everything changes, yet nothing is lost. As stars recycle and galaxies merge, so too do moments in your own life transform and return in new forms. All things, from atoms to galaxies, evolve toward equilibrium and renewal. If you could step outside the flow of time and watch the universe unfold, you would see galaxies moving like slow tides across an endless ocean. Their motion is graceful but imperceptible on human scales. 1 billion years to a galaxy is as a breath to the cosmos. To us, it feels frozen, yet every cluster drifts, every star shifts, and every atom changes. In this slow drift lies a profound lesson. Time moves differently depending on where and how you look at it. Einstein's theory of relativity showed that time and space are not separate. They form a single continuum, space-time, that bends with gravity and stretches with motion. In strong gravitational fields, such as near a black hole, time slows relative to regions of weaker gravity. Likewise, an object moving at high speed experiences time more slowly than one at rest. This is not illusion but measurement. Experiments with atomic clocks on satellites confirm that time's flow depends on velocity and gravity. In physics, this phenomenon is called time dilation, and it shapes everything from GPS navigation to the aging of stars. On a cosmic scale, time dilation becomes a lens through which astronomers view the universe. When light from distant galaxies travels toward us, space itself expands, stretching the wavelength of that light and lengthening the time between each photon's arrival. Events that once unfolded rapidly now appear to move slowly. The flicker of a supernova, the pulse of a distant quasar, all seem to linger. Observing the deep universe is like watching time itself drift into repose. The farther we look, the slower it becomes, until it appears almost still. This slowing of cosmic events parallels the slowing of the human mind as it prepares for rest. In wakefulness, thoughts race, attention leaps, and time feels fragmented. As you relax, neural activity synchronizes. Waves in the brain lengthen and become more rhythmic. Perception stretches, thoughts drift apart, and moments merge into continuity. Physically, time does not slow, yet subjectively it feels as if it does. The brain, like the cosmos, expands its internal space for stillness. Each breath becomes a galaxy's orbit, each heartbeat the slow revolution of a star. Scientists measure the universe's expansion through redshift, but you can measure your own stillness through rhythm, the length of breath, the steadiness of pulse, the calm unfolding of thought. The principle is identical. Motion defines time. When motion slows, time softens. Just as a galaxy moving away from us appears to drift more slowly, your awareness, pulling away from waking urgency, enters a slower orbit. The physics of calm is written in the same mathematics as the physics of light. If the universe is a vast ocean of time, you are a wave upon its surface, small, transient, but made of the same water. The atoms in your body obey the same equations that govern cosmic expansion. Even as you lie still, you are part of motion measured in billions of years. You do not move through time alone. Time moves through you. The chemical reactions in your cells, the electric pulses in your brain, all tick in harmony with the universal clock, a clock that began with the first expansion and continues unbroken. In this understanding lies deep serenity. The passage of time is not something to resist or fear. It is the current that carries all existence forward. The galaxies drift, the stars burn, the atoms vibrate, and you breathe. Everything flows together through the same continuum. To rest is to join the slow rhythm of the universe, to become part of its gentle drift through eternity. So, as you settle into stillness, imagine the galaxies above you not as fixed points, but as travelers in a long, slow migration. They move silently through expanding space, their light reaching you after unimaginable ages. In their unhurried pace, they embody the peace that time offers when we stop trying to measure it. Let your thoughts drift as they do, patient, weightless, unbound. The same fabric of space-time that carries galaxies also cradles you. You are drifting too, gently, through time. If you could step far enough back to see the entire universe at once, the view would not resemble empty space but a vast and delicate network, an intricate web of light and shadow spanning unimaginable distances. Galaxies are not scattered randomly through the cosmos. They are arranged along immense filaments of matter, intersecting at dense nodes where galaxy clusters form. Between these filaments lie enormous voids, regions almost empty, stretching hundreds of millions of light-years across. Together, These filaments and voids create what astronomers call the cosmic web, the universe's largest visible structure. This pattern emerged from the smallest irregularities in the early universe. After the Big Bang, matter and radiation were nearly uniform, with only tiny fluctuations in density. Gravity amplified those fluctuations, pulling slightly denser regions together while emptier regions expanded faster. Over billions of years, this subtle imbalance grew into an immense architecture. Gas, dust, and dark matter flowed along invisible gravitational channels, forming the filaments that now thread across space. Where filaments intersect, galaxies collect like dew along a spider's web. Dark matter plays the leading role in this grand design. Its gravity dictates where ordinary matter gathers, guiding the formation of galaxies and clusters. Though invisible, it shapes everything we see. Simulations such as the Millennium Run and Illustris project recreate the cosmic web in digital form, revealing a universe alive with motion and connection. The results are astonishingly beautiful. Tendrils of light forming bridges between clusters, voids stretching like calm oceans between glowing shores. Even the emptiness has pattern. Even darkness follows law. At smaller scales, the same structure repeats. Galaxies connect through filaments of gas, transferring material and energy across millions of light years. These intergalactic highways feed star formation, recycling matter from dying galaxies into newborn systems. The web is not static, it flows. Matter moves continuously through it, reshaping the architecture of the universe as time unfolds. The cosmic web is the scaffolding on which evolution occurs, the framework that gives the universe both form and balance. To study the web, astronomers combine data from surveys of galaxy positions, quasar absorption lines, and cosmic background maps. By measuring redshifts and mapping density fields, they reconstruct three-dimensional models of structure across billions of light years. The patterns that emerge are mathematical and organic at once. The distribution of galaxies follows the same statistical laws found in rivers, neurons, and cloud formations. Nature, it seems, repeats its geometry across scales, from the microscopic to the cosmic. This revelation carries a quiet grace. The universe, in its vast complexity, organizes itself through simple principles: gravity pulling, expansion stretching, energy flowing toward equilibrium. No single force commands the design. Instead, balance emerges naturally, the way ripples on water form and fade without instruction. The cosmic web demonstrates that order can arise from chaos, that beauty is not imposed but inherent in the fabric of physics. For the human mind, the scale of this structure is almost incomprehensible. Light itself takes billions of years to cross a single filament, yet the same geometry can be traced in the branching of trees, the wiring of the brain, and the circulation of rivers. The web outside mirrors the networks within. Each neuron, each capillary, follows similar laws of efficiency and flow. You are not separate from that pattern. You are a smaller version of it, a local expression of the same universal symmetry. As you rest, imagine yourself suspended within this vast web, your body one of countless nodes connected by invisible threads. Between every heartbeat and every breath, the same balance exists: motion and stillness, density and emptiness, tension and release. The cosmic web is not a distant structure. It is a reflection of the harmony that underlies all things. Let its quiet geometry remind you that even in emptiness, there is connection. Even in silence, there is form. The universe holds itself together not through force, but through balance, and so do you. No matter how powerful our telescopes become, there will always be a horizon beyond which we cannot see. The universe is vast, but not infinitely visible. Light travels at a finite speed, and space itself has only existed for a finite time. The result is a natural boundary to observation, the cosmic horizon, the edge of the observable universe. Beyond that horizon, light has not had enough time to reach us since the beginning of cosmic expansion. What lies past it remains real but forever hidden, like a coastline glimpsed through fog that never lifts. The speed of light, about 300,000 kilometers per second, defines the ultimate limit of information. Nothing can move faster. When astronomers observe distant galaxies, they are looking not at the present, but at the past. A galaxy 10 billion light-years away shows us how it appeared 10 billion years ago. At greater distances, light stretches as space expands, shifting toward red. Eventually, expansion stretches it so far that the wavelengths grow longer than the detectors we build. Those signals fade into darkness, not because they are gone, but because time itself has carried them beyond reach. This fading is not a failure of instruments, but a law of nature. The universe expands faster than light can traverse it at extreme distances. Beyond a certain point, known as the cosmological event horizon, no signal sent toward us today will ever arrive, no matter how long we wait. Galaxies beyond this limit continue to exist, forming stars and evolving, but their light will never again touch us. The cosmos is thus divided into regions connected by light and others separated by expansion, each isolated by the very fabric of space-time. Astronomers estimate that the observable universe extends about 46 billion light-years in every direction. That figure is larger than the product of the universe's age, multiplied by the speed of light, because space has been expanding during the journey of the photons. It is as if the stage grew while the performance continued. Beyond this sphere lies an unobservable vastness, perhaps more galaxies, perhaps something entirely different. The total universe could be infinitely larger, yet only this portion is available to observation. Despite these boundaries, the edge of visibility is not empty of meaning. It is filled with the faint radiation of the cosmic microwave background, the oldest light we can detect, coming from the time when the universe became transparent. That radiation forms a perfect spherical shell around us, marking the limit of what light can reveal. When we look deep into space, we are also looking back through time, tracing the history of matter and energy toward their origin. Every direction points to the past, and the edge of observation marks the beginning of time as we can know it. These limits remind us that knowledge, no matter how vast, will always coexist with mystery. The observable universe is not all that exists, it is merely the portion we can reach with light and reason. The unseen beyond is not void but continuation, an unending expanse that humbles the mind and deepens the meaning of what we can know. Science does not erase mystery, it defines where it begins. For the human mind, the cosmic horizon mirrors our own perception. Just as light defines what can be seen, awareness defines what can be understood. Beyond that boundary lie possibilities not yet imagined. The limit of vision is not confinement, but invitation, a frontier encouraging discovery. So as you rest, imagine yourself standing at that edge of visibility. The galaxies within reach glow faintly around you, while beyond them stretches an ocean of darkness that hides not absence but potential. Every breath, every thought is an act of observation within your own horizon of consciousness. And just as astronomers accept what they cannot see, you too can find peace in the unseen, knowing that the unknown is not emptiness, but part of a larger whole waiting quietly beyond the light. The observable universe feels boundless, yet even it might be only one region in a far greater reality. Modern cosmology entertains a bold idea that our universe could be one of many, a member of a vast ensemble called the multiverse. Each universe within it may have different physical laws, constants, or dimensions. These are not fanciful speculations, but scientific possibilities born from attempts to explain the conditions that gave rise to everything we know. The most prominent concept arises from cosmic inflation, a theory describing how the early universe expanded exponentially in a fraction of a second after the Big Bang. According to this model, inflation may not have ended everywhere at once. Some regions stopped inflating and formed universes like ours, while others continued expanding, spawning new bubble universes endlessly. Each bubble would be self-contained, with its own space-time and possibly its own laws of physics. From the outside, one would never see another bubble. They are separated by regions still inflating faster than light can bridge. In this vision, the multiverse is an ever-growing foam of universes floating in a larger cosmic sea. A second idea comes from string theory, which attempts to unify gravity with quantum mechanics. It predicts that the universe has many dimensions, not just the familiar 3 of space and 1 of time, but possibly 10 or 11. In some models, our universe exists on a 3-dimensional brane embedded within a higher dimensional space. Other branes could exist parallel to ours, each holding its own universe. Rare interactions between these branes might even cause phenomena like the Big Bang, collisions in higher dimensional space, giving birth to new realities. These ideas extend mathematics beyond human experience, yet they remain consistent with what we know about energy, geometry, and the flexibility of space-time. A third perspective comes from quantum mechanics, particularly the many worlds interpretation. It proposes that every quantum event, every decision, decay, or measurement branches into multiple outcomes, each realized in a separate, non-interacting universe. In this view, reality continuously divides, creating a limitless number of parallel versions of history. Every possibility exists somewhere, each following its own consistent timeline. Though largely philosophical, this interpretation preserves the deterministic nature of quantum laws while accounting for their apparent randomness. Testing these ideas is extremely difficult. By definition, universes beyond our own would be separated by physical barriers or laws that prevent contact. Still, scientists search for indirect evidence. Collisions between inflationary bubbles could, in theory, leave subtle imprints on the cosmic microwave background, visible as circular anomalies. Researchers analyze sky maps for such patterns, though none are confirmed. Other physicists explore mathematical predictions from string theory or investigate quantum decoherence, the process by which parallel outcomes become distinct, for hints of branching realities. Each approach edges closer to a question that may never have a final answer. The multiverse, if real, expands more than the scale of existence. It transforms its meaning. It suggests that the constants of nature, the speed of light, the charge of the electron, the strength of gravity, may not be uniquely tuned for our universe, but simply part of a larger range of possibilities. Our existence, then, becomes one expression among countless others, not privileged but remarkable nonetheless. The improbability of life feels less like a miracle and more like the natural outcome of infinite trials. To contemplate this is both humbling and liberating. We may never know if other universes exist, yet their possibility reflects the same curiosity that drives all science, the refusal to accept boundaries as final. The human mind, like the cosmos, seeks to expand, to imagine what lies beyond its horizon. Whether or not the multiverse is real, it teaches us that reality is broader than our perception and that imagination is an extension of discovery. So as you rest tonight, think of yourself not as small, but as part of an expanding field of possibilities. Each breath, each thought, could be seen as one thread among countless parallel paths, all flowing outward into infinity. The unknown beyond your awareness is not emptiness but continuation, a silent promise that there is always more to discover, even beyond the edges of time and space. To understand the universe's beginning, one must look not outward but inward, into the quantum realm, where matter and energy blur into uncertainty. Quantum physics describes the behavior of particles so small that their positions and motions can never both be known precisely. Instead of certainties, there are probabilities. Instead of fixed trajectories, waves of potential. Out of these fluctuations, cosmologists believe, the universe itself was born. During the earliest fraction of a second after the Big Bang, the universe was unimaginably dense and hot, its energy condensed into a uniform field. Quantum effects ruled everything. Within this field, quantum fluctuations, tiny random variations in energy, constantly appeared and vanished. Normally, such fluctuations cancel each other out, leaving space nearly smooth. But when cosmic inflation began, these minute irregularities were stretched to cosmic scales. What had been smaller than an atom suddenly spanned light years, frozen as faint ripples in the density of matter and energy. Over billions of years, gravity amplified those ripples, forming galaxies, stars, and eventually planets. The grand structure of the cosmos, in all its vastness, traces back to random tremors in the quantum foam. This idea bridges the smallest and largest realms of physics. The same uncertainty that governs electrons within atoms shaped the distribution of galaxies across the universe. It means that everything we see, the Milky Way, the Sun, even life itself, arose from fluctuations once smaller than a proton. These were not designed or planned, they were natural expressions of quantum law. When inflation stretched the universe, it also locked those random patterns into the cosmic microwave background, leaving a subtle fingerprint that satellites like Planck have measured with exquisite precision. The pattern of warm and cool spots across the sky is, in essence, a snapshot of quantum noise, amplified into galaxies. At the heart of quantum theory lies a principle known as the Heisenberg uncertainty principle, which states that certain pairs of properties, like position and momentum, cannot both be measured exactly at the same time. This is not a limitation of instruments, but a fundamental property of reality. The universe does not exist as a fixed state until interaction occurs. Instead, it unfolds through probabilities, collapsing into measurable form only when conditions allow. The early universe operated under this principle universally. Everything that exists today emerged from a field of uncertainty resolving into stability. Quantum physics also introduces the concept of vacuum energy. Even in perfect emptiness, virtual particles appear and disappear continuously, borrowing energy from nothing and returning it almost instantly. This restless vacuum might have triggered inflation itself, providing the pressure that drove the universe's exponential growth. If so, the cosmos began not from nothingness but from the natural tendency of quantum fields to fluctuate. Nothing, in the quantum sense, is never truly nothing. It is a sea of potential waiting for release. For scientists, connecting quantum mechanics to cosmology remains one of the greatest challenges. General relativity explains the large-scale behavior of space-time, while quantum theory governs the microscopic world. At the singularity of the Big Bang, both sets of rules apply, yet they currently resist unification. The search for a quantum theory of gravity aims to describe that earliest instant, when time and space themselves may have emerged from a deeper, probabilistic state. The answers could reveal not just how the universe began, but why physical laws take the forms they do. And yet, even without full understanding, the story carries quiet wonder. The randomness of quantum fluctuations does not mean chaos, it means freedom. From uncertainty came structure, from probability came stars. The universe was never planned, yet it organized itself with mathematical precision, guided by laws that require no designer beyond consistency itself. As you rest, imagine those ancient fluctuations, tiny waves of energy trembling in silence. Each crest and trough carried the potential for everything that would one day exist, including you. The atoms in your body, the thoughts in your mind, all descend from patterns written in quantum noise. You are part of that first ripple still unfolding, a continuation of the same vibration that began the cosmos. Let that realization ease you into stillness. Even randomness can lead to harmony, and from uncertainty all order arises. Among all the mysteries of the cosmos, few inspire more awe than the precision of its design. The universe operates according to a small set of physical constants, fixed quantities that define the strength of gravity, the speed of light, the charge of the electron, and the masses of fundamental particles. These numbers never change. They determine how atoms form, how stars burn, and how galaxies hold together. If even one of them differed slightly, the universe as we know it could not exist. Physicists often refer to this delicate balance as fine-tuning. It is not fine-tuning by intent or hand, but by natural precision. The gravitational constant, for instance, is weak compared to the other fundamental forces. Were it stronger, stars would collapse rapidly into black holes. Weaker, and they would never ignite. The electromagnetic force binds electrons to nuclei. If altered even minutely, atoms might not hold together or would combine too easily, leaving no chemistry. The strong nuclear force, which glues atomic nuclei, must sit within an extraordinarily narrow range. A slightly weaker strength, and hydrogen could not fuse. Slightly stronger, and all hydrogen would vanish into heavier elements, leaving no water, no stars, no life. These constants define the very possibility of structure. Their values, expressed through equations like Einstein's field laws and the Schrödinger equation, allow the universe to exist in a state of long-term stability. In the language of physics, it is an improbable but self-consistent configuration. To scientists, this is not coincidence to be admired, but a question to be explored. Why these numbers and not others? Some see the fine-tuning problem as evidence that countless universes exist, each with different constants. In such a multiverse, we find ourselves in one where conditions happen to permit life, not because it was designed that way, but because life could arise nowhere else. Others search for a deeper theory that shows these constants are not arbitrary but inevitable, locked by symmetry or necessity. The search continues through experiments in particle physics, cosmology, and string theory, where the hope is that the universe's mathematical structure will reveal why reality chose such precise values. What makes fine-tuning remarkable is not just its improbability, but its consistency. The same constants that govern the behavior of electrons in a laboratory also describe the dynamics of galaxies billions of light-years away. The universe, vast and ancient, follows the same rules everywhere and everywhen. A hydrogen atom in your bloodstream vibrates under the same laws as the hydrogen glowing in a distant star. This unity of principle gives physics its extraordinary reach. It also reveals that the cosmos is not chaotic, it is lawful, coherent, and stable across every scale of existence. For human beings, that order has profound implications. It means the conditions for consciousness and life are not fragile accidents but natural outcomes of physical harmony. We exist because balance is woven into the foundation of reality. The forces that bind galaxies also bind thought. The same constants that hold the nucleus of an atom steady hold the mind within the quiet boundary of awareness. Stability is not something imposed, it is something the universe achieves by being precisely itself. Even in this precision, there is room for wonder. The constants do not explain why they are what they are, only that they must be so for the universe to exist as it does. Science may one day uncover the mechanism behind their values, but perhaps their deeper meaning lies in what they allow: complexity, structure, and awareness. The harmony of numbers becomes the harmony of being. As you breathe now, you are participating in that equilibrium. Each molecule of oxygen entering your lungs obeys the same constants that govern the stars. Gravity keeps you anchored, electromagnetism carries the breath through your bloodstream, and quantum fields sustain the bonds within your cells. You are, in a precise sense, an equation written in atoms and time, a small but perfect solution within the larger problem of the universe. In the balance of constants, existence itself finds its rhythm, and within that rhythm, peace. Life is not separate from the universe, it is one of its natural expressions. The same physical laws that shape galaxies also shape cells. The same elements that form distant stars form your body. From the perspective of chemistry, there is no boundary between the living and the cosmic. The story of life is simply the story of matter, arranged in a way that can copy itself, respond to its surroundings, and remember what works. The essential ingredients of life are carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These 6 elements form the foundation of all known biological molecules, from DNA and proteins to the sugars that power cells. Each of them was created in stars. Hydrogen was born in the first moments after the Big Bang, and helium soon followed. But carbon and oxygen required stellar furnaces, where intense heat and pressure fused lighter atoms into heavier ones. When massive stars reached the ends of their lives, they scattered these elements through supernova explosions, enriching space with the building blocks of life. Later generations of stars and planets formed from that enriched material, carrying within them the seeds of potential chemistry. On Earth, those elements combined in water, a molecule so simple, yet so crucial. Water's unique properties, like its ability to dissolve many substances and regulate temperature, made it an ideal medium for complex reactions. Over time, organic molecules began to assemble into structures capable of replication and metabolism. These early chemical systems evolved into cells, forming the first living organisms. The path from hydrogen atoms to consciousness may seem long, but it follows an unbroken chain of physical cause and effect. Biology is chemistry made intricate. Chemistry is physics made slow. Scientists have found organic molecules in interstellar clouds and on comets, suggesting that life's chemistry began not on Earth alone but across the galaxy. Amino acids, the building blocks of proteins, have been detected in meteorites. This discovery implies that the basic ingredients of life form naturally wherever the right conditions exist. The laws of physics make carbon-based complexity almost inevitable. Given enough time and energy, matter organizes itself into patterns that feed, grow, and think. Even the human body reflects the composition of the universe. Roughly 2/3 of its atoms are hydrogen, formed in the Big Bang. The rest were forged in stars long before the solar system existed. Every breath you take returns oxygen to the atmosphere that another organism will one day use. Every heartbeat depends on the same electrochemical principles that power lightning in clouds. The rhythm of life echoes the rhythm of matter, the same pattern repeated at different scales. In a broader sense, life can be seen as the universe learning to observe itself. Consciousness transforms physical matter into awareness, allowing atoms arranged in neural networks to reflect on the stars they came from. This self-awareness is not separate from physics, it is its continuation. The laws that allowed galaxies to form also allowed you to wonder about them. Through you, the universe recognizes its own existence. Life's chemistry also teaches humility. It reminds us that intelligence, emotion, and imagination arise not from something added to matter, but from matter's own potential for complexity. The universe did not need special permission to create life. It simply followed its rules to their natural conclusion. Within those rules lies enough richness to produce everything from crystal lattices to consciousness. The difference is not in kind but in degree, structure growing into function, and function into thought. So, as you rest, imagine the atoms within you remembering their journey, forged in ancient stars, cooled in clouds of dust, shaped into oceans and cells, and finally gathered here, breathing softly. You are a pattern of cosmic chemistry in motion, balanced between the micro and the infinite. Every moment of rest renews that balance, just as the universe renews itself through cycles of creation and decay. To be alive is to participate in that eternal chemistry, a quiet, ongoing reaction between matter and meaning. Our solar system is a small but intricate expression of cosmic order, a collection of worlds formed from the same swirling cloud that gave birth to the Sun. About 4.5 billion years ago, a vast nebula of gas and dust collapsed under gravity, perhaps triggered by the shockwave of a nearby supernova. As the cloud contracted, it spun faster, flattening into a disk. At its center, matter gathered and ignited nuclear fusion, creating the Sun, a self-sustaining furnace that has burned steadily ever since. Within the disk, smaller clumps of material began to collide, merge, and grow into the planets, moons, and asteroids that orbit today in silent harmony. The Sun contains more than 99% of the solar system's mass, yet its gravity allows the rest to dance in stable motion around it. The innermost planets, Mercury, Venus, Earth, and Mars, formed from rocky materials that could withstand the Sun's heat. Farther out, where temperatures were lower, volatile compounds like water and methane could freeze, creating the massive gas giants Jupiter and Saturn, and the icy worlds Uranus and Neptune. This distribution of elements is a direct imprint of temperature gradients in the early solar nebula, a natural sorting of matter by distance and heat. Each planet carries a distinct history, a unique experiment in the chemistry of worlds. On Earth, conditions aligned to produce liquid water, a protective atmosphere, and the cycles that sustain life. Mars once had rivers and a thicker atmosphere, traces of which remain etched in its red surface. Jupiter's immense gravity may have shielded the inner planets from excessive asteroid impacts, while its moons, like Europa and Ganymede, hold vast subsurface oceans that may still harbor primitive life. Even the smallest bodies, comets, asteroids, and Kuiper Belt objects, preserve the ancient material from which the planets formed, acting as time capsules of the solar system's youth. To study our solar system is to study the laws that shape all planetary systems. The same processes occur elsewhere in the galaxy. Gas clouds collapsing into stars, dust forming disks, and gravity sculpting order from chaos. Observations from telescopes like Kepler and TESS have revealed thousands of exoplanets, some orbiting suns very different from our own. Many lie in habitable zones, where temperatures allow liquid water to exist. The diversity of these systems suggests that planet formation is not rare but universal, another step in the universe's unfolding toward complexity. What makes the solar system a laboratory is not just its mechanics but its accessibility. Here, we can touch the evidence, the meteorites that fall to Earth, the data from robotic probes visiting distant moons, the light reflected from icy rings. Every mission, from Voyager's journey beyond the outer planets to the rovers on Mars, adds to a single, continuous experiment, an exploration of our origins written across billions of kilometers. The laws discovered here apply everywhere, reminding us that our corner of space is both ordinary and extraordinary at once. The Sun itself remains a living reminder of the universe's power to sustain equilibrium. Through the process of nuclear fusion, it converts hydrogen into helium, releasing energy that radiates across space. That energy warms Earth, drives its climate, and powers the photosynthesis that sustains life. The balance between gravity and radiation within the Sun mirrors the balance that holds all systems stable: compression countered by expansion, inward pull met by outward flow. At night, when you look up at the stars, remember that every one of them hosts its own system of worlds, some still forming, others long gone. The solar system is not an exception but an example, one note in the symphony of cosmic evolution. Its order is a reflection of universal principles: gravity's patience, matter's persistence, and time's quiet sculpting hand. As you close your eyes, think of those orbits continuing, planets circling in silence, asteroids drifting in cold arcs, comets tracing long ellipses through darkness. Nothing in the solar system hurries, yet everything moves. Its rhythm is the same rhythm that carries you toward rest, steady, predictable, and calm. You are part of that motion, one more traveler on a small, luminous world, turning endlessly beneath the light of its star. The universe never stands still. Every planet, every moon, every atom moves according to invisible laws that keep the whole in balance. Earth itself turns at nearly 1,000 miles per hour at the equator, orbiting the Sun at immense speed, while the Sun drifts within the Milky Way, which itself moves through expanding space. To us, these motions feel like stillness, because they are constant, graceful, and perfectly synchronized. The same principle governs the body in rest, continuous movement beneath the surface, so steady it becomes calm. From the perspective of physics, motion and balance are inseparable. Objects in motion stay in motion unless acted upon by another force. This inertia keeps planets in orbit just as it maintains the flow of blood through your veins or the steady rhythm of your breathing as you drift into sleep. Gravity provides the counterbalance, the invisible hand that curves straight paths into orbits, preventing chaos. In the body, chemical and electrical signals serve the same role, ensuring that energy circulates evenly, that cells communicate, that systems remain in equilibrium. If you could observe your own body from the scale of atoms, you would see constant activity. Electrons orbit atomic nuclei, proteins fold, ions flow across membranes, a ceaseless choreography, as intricate as any solar system. Sleep does not end these motions, it brings them into harmony. Metabolism slows, but organization increases. Neural pathways consolidate memory, muscles repair, and the body recalibrates. Like celestial systems, you find stability not in stillness, but in rhythm. The planets provide a perfect example of sustained balance through motion. Their orbits are ellipses, paths defined by the interplay between gravity's pull and inertia's persistence. Too close to the Sun, a planet would fall inward; too far, and it would drift away. The same precision exists in your biological rhythms. The heart's contractions, the rise and fall of breath, the cyclical release of hormones, all rely on feedback loops that keep you poised between activity and rest. Disrupt that rhythm, and you lose balance. Restore it, and calm returns naturally. Astronomers describe orbital resonance as a condition where planets or moons move in rhythmic ratios, one completing 2 revolutions while another completes 3. This synchronization creates stability within systems that might otherwise fall apart. In a similar way, your mind and body rely on internal resonances. Brain waves shift into slower patterns during rest, matching the heartbeat's rhythm and the timing of breath. When these frequencies align, consciousness enters a state of coherence, the biological equivalent of an orbital harmony. The mathematics of motion is universal. Whether describing planets or neurons, the same laws of energy conservation, feedback, and equilibrium apply. This unity is more than coincidence. It is evidence that order scales across dimensions. The cosmos balances its forces through gravity and expansion, while the body balances its processes through feedback and flow. In both, peace arises not from absence of motion but from motion that repeats predictably, endlessly, without struggle. As you breathe now, notice the quiet rhythm guiding you. Each inhale pulls energy inward, like a planet drawn by gravity. Each exhale releases, like a planet carried forward by inertia. The balance between the two is not forced, it is simply maintained, the way celestial orbits maintain theirs through the steady curve of space-time. The peace you feel is not separate from the physics of the universe. It is its reflection within you. Let your thoughts drift outward now, following that invisible symmetry. Imagine your breath as an orbit, circling gently around stillness, never stopping, never breaking. You are part of a system so vast that even rest participates in motion. The same principles that keep galaxies from collapsing guide your heartbeat, your breath, your dreams. In this harmony of motion, you are both still and traveling, a quiet planet turning through space, perfectly balanced in the dark, at peace with the rhythm of the universe. Every star that shines today carries within it the promise of an ending. The cosmos is filled with light only for a time. As hydrogen and helium burn in stellar cores, energy radiates outward, keeping darkness at bay. But fuel is finite, and the universe's expansion ensures that, eventually, all that energy will be spent. What remains is not destruction, but transition, the long, slow cooling of everything that ever was. Astrophysicists divide the universe's life into eras. We live now in what they call the stelliferous era, the age of stars. It began when the first luminous objects ignited hundreds of millions of years after the Big Bang, and it will continue for trillions more. During this period, galaxies shimmer with new light as hydrogen fuses into heavier elements. Over time, the rate of star formation will decline as fuel runs out. The brightest stars will die first, followed by smaller, steadier ones. The sky will slowly fade, not all at once, but star by star. When the final generation of stars exhausts its fuel, the universe will enter a quieter age, the degenerate era. White dwarfs, neutron stars, and black holes will dominate the landscape. These remnants are matter in its most stable forms, cooled and compressed, shining faintly with residual heat. Over unimaginable timescales, even white dwarfs will cool to darkness, becoming black dwarfs, cinders of former suns, radiating no visible light. The once luminous universe will turn transparent, a place where energy moves only as long, slow radiation across near-empty space. In this distant epoch, gravity will continue to act, stellar remnants will merge, collide, and sometimes feed black holes. Galactic collisions will still occur, though at slower pace, eventually consolidating matter into isolated systems adrift in expanding void. Black holes will dominate, quietly consuming what remains of mass, yet even they are not eternal. Through Hawking radiation, they will lose energy particle by particle, fading into nothing over vast spans of time. When the last black hole evaporates, the universe will consist of low-energy photons and sparse particles drifting through endless darkness. Beyond that lies the dark era, a time when matter itself may decay. Protons, the building blocks of atoms, could eventually break apart, though no one knows for certain. If they do, even the most stable structures will dissolve into subatomic debris. Space will become a thin bath of particles, evenly distributed, with no gradients of temperature or density. This is the final approach to thermodynamic equilibrium, where entropy reaches its maximum and no energy remains to fuel change. It is not a dramatic ending, but a fading, a universe approaching perfect stillness. To some, this vision feels melancholic, but it is also deeply serene. The laws of physics do not fear endings, they complete cycles. Just as a star's death scatters elements for new worlds, the universe's eventual quiet marks the fulfillment of its natural trajectory. Motion becomes balance, energy becomes rest. The cosmos does not vanish. It transforms into a uniform calm, a final equilibrium that honors every process that came before. This future reminds us that transience is not failure but continuity. Stars burn because they cannot last forever. Life thrives because it exists between creation and decay. The same principle governs human existence. You breathe in energy, release it, and return it to the system that supports you. Rest follows effort, just as darkness follows light. The rhythm of the universe mirrors the rhythm of being. As you drift into stillness, imagine that distant future, a cosmos at rest, its stars long gone but its order intact. The space around you, the air you breathe, the warmth of your body are all part of that same process, scaled to human time. You are made of matter that once blazed and will one day cool again, yet nothing of it will truly disappear. Energy changes form, structure changes meaning. The universe began in motion and will end in quiet, and in both there is peace. Long after stars fade and galaxies dissolve, the universe will still hold something less tangible but no less real: information. Every particle's position, every quantum interaction, every burst of radiation carries data about what once was. Physics teaches that energy and information are never truly lost. They change form, encoded in the evolving structure of space-time itself. In this way, the universe remembers. When a photon travels from a star to your eye, it carries the story of that star's surface, its temperature, motion, and composition. The spectrum of that light is a record of atomic transitions that occurred millions or billions of years ago. Even after the star is gone, the photon continues its journey, carrying that information forward. The night sky is not just a view of distant worlds, it is a vast archive of memory written in light. Each glimmer above you is history arriving in real time. This principle extends beyond light. Every process that occurs leaves a trace in the fabric of reality. According to the law of conservation of information, the total information content of the universe remains constant, even as matter transforms. In quantum mechanics, particles that interact become entangled, their states linked across distance. Measuring one instantaneously influences the other, no matter how far apart they are. The universe, at its deepest level, is a web of such entanglements, an interconnected memory field that preserves relationships even when their participants move apart. Black holes once seemed to challenge this principle. If matter and information fell into them and could never escape, it would mean the universe could forget. Yet theories of Hawking radiation suggest otherwise. As black holes evaporate, the information about what fell in appears to be encoded in the radiation that escapes. The process is slow and subtle, but it restores balance. Nothing, it seems, is truly erased, only rearranged into new forms. Information is conserved because physics itself is reversible at the most fundamental level. Even at cosmic scales, memory persists. The distribution of galaxies reflects quantum fluctuations from the dawn of time. The faint ripples in the cosmic microwave background are imprints of those first moments, frozen into radiation that still bathes all of space. To study the universe is to study its memory, a record not written in words or symbols, but in temperature, density, and light. Every atom, every photon, is a piece of that archive. For living beings, memory functions on a similar principle. Neurons store information through changes in molecular structure, encoding experiences as patterns of electrical and chemical activity. The process mirrors the cosmos on a smaller scale, energy shifting form to preserve knowledge. When you recall a memory, you are reading data written by your own biology. The universe remembers through physics, you remember through biology. Both rely on the same foundation, the persistence of pattern. The idea that information endures offers comfort when contemplating cosmic impermanence. Even as stars burn out and galaxies drift apart, their stories continue in radiation, in the curvature of space-time, in the laws that describe them. The cosmos does not forget its past. It evolves through it. Each transformation adds to the total record, enriching a history written not in ink, but in energy and order. As you close your eyes tonight, you might think of light as thought, traveling, dispersing, but never vanishing. The warmth on your skin from the sun is memory made tangible, the same energy that once formed stars and will someday return to the void. The universe is not losing itself, it is remembering differently. Every photon, every vibration, every breath participates in that remembrance. You are part of this continuity. The atoms in your body once recorded the fusion of ancient stars. The light you see tonight carries their echo. When you rest, you too join the memory of the universe, a fleeting, conscious expression of energy that will continue in other forms long after. The cosmos does not forget, it simply keeps moving, carrying everything forward in the gentle flow of time and light. In a universe so vast that its boundaries may never be known, human life might appear small. Our planet orbits an average star in one of hundreds of billions of galaxies, each containing countless suns. Yet scale does not define significance. What makes existence remarkable is not its size but its capacity for awareness. Through the lens of consciousness, the cosmos observes itself, and through curiosity, it begins to understand. Every scientific discovery, from the orbit of planets to the structure of atoms, represents matter learning about its own nature. The brain that contemplates the stars is built from elements forged within them. When you look at the night sky, the photons entering your eyes have traveled for millions of years only to end their journey by creating a thought. In that instant, the universe completes a circle, energy turned into awareness. You are not apart from the cosmos, you are one of its ways of knowing. This perspective transforms the idea of insignificance. It reveals that consciousness is not an accident but a property that emerges naturally when matter organizes itself with enough complexity. Neurons and galaxies both follow the same physical laws, systems governed by energy, motion, and feedback. Awareness may be rare, but it is not unnatural. It is a continuation of the same pattern that governs everything: structure seeking equilibrium, complexity arising from simplicity. The universe does not think as we do, but through us, it contemplates its own laws. The search for meaning, then, becomes a reflection of physics itself. Just as particles seek lower energy states, the mind seeks understanding. Curiosity is the human expression of entropy, the drive toward equilibrium through knowledge. Each question answered brings temporary balance. Each mystery unresolved invites new motion. Science, philosophy, and art are all extensions of this process, converting uncertainty into insight and returning the energy of wonder back into the world. Seen from this view, purpose is not something imposed upon life from outside, but something generated within it. Meaning is a pattern, not a decree, an arrangement of thought and experience that reflects the structure of the universe. Gravity shapes galaxies, consciousness shapes perception. Both emerge from the same tendency of nature to create order from possibility. To find purpose in the vastness of space is not to claim special privilege, but to recognize participation. We are part of the process, active within it. Even emotion finds its place in this framework. Love, fear, hope, and awe are forms of energy, responses to connection and uncertainty. They arise from the same physical reality that governs light and gravity. When you feel wonder at the night sky, it is because your mind is tuned to patterns that mirror the universe's own. The rhythm of your heartbeat aligns with the rhythm of motion around you. In that sense, the experience of meaning is itself a resonance, a harmonic between awareness and the laws that make awareness possible. If one were to measure humanity by cosmic scale, our lifespan would seem brief. Yet within that briefness lies intensity, a compression of time that gives each moment weight. The universe may last forever, but only consciousness can give it reflection. In observing it, you make it visible. In understanding it, you give it form. The cosmos has no voice, but through thought, it speaks. So as you rest, think of yourself not as small but as necessary. The same laws that shape galaxies also shaped your mind. Your awareness is the light of the universe turned inward, a moment of clarity in its vast unfolding. When you breathe, you echo the rhythm of stars collapsing and reforming. When you dream, you mirror the infinite combinations of possibility within quantum space. You are the universe thinking about itself, and in that realization lies both humility and peace. As the story of the cosmos stretches forward, there is no final act, only a soft continuation. The universe does not end with a sound or a boundary. It fades, balances, and carries on in ways too slow for any observer to follow. What began as light and motion becomes quiet equilibrium. The night sky you see above you is not darkness but distance, light so far away that it has not yet arrived. To look at it is to look into time itself, and to understand that rest is not absence, but persistence at peace. Sleep follows the same principle. When you drift into it, your mind does not stop. It reorganizes, resets, and redistributes its energy. Neurons settle into harmony, memories weave together, and consciousness relaxes into the quiet rhythm of biology. The body cools, heart rate slows, and energy flows evenly through the systems that sustain life. It is not an end to awareness, but a recalibration, a personal version of the universe's long, slow balance. The physics of sleep and the physics of stars both express the same law: energy seeking rest, motion finding rhythm. The endless night of the universe is not a void to fear, but a vast equilibrium waiting beyond change. Long after stars have dimmed, radiation will still move, carrying traces of the past through space. Even when the last particles drift apart, the laws that guided them will remain, timeless and complete. Those laws, symmetry, conservation, balance, are the same principles that guide every heartbeat, every breath, every thought. In this way, the universe never truly becomes silent, it simply settles into its most peaceful form. Astronomers describe the universe's fate as a gradual cooling, a slow diffusion of energy until everything approaches the same temperature. In that stillness, time itself will lose meaning because nothing will change enough to mark its passage. Yet even then, physics persists, defining structure without motion, possibility without activity. The universe will rest the way the body rests after a long day, not extinguished, but fulfilled. To contemplate this is not to face emptiness, but completion. Every process, the birth of stars, the shaping of worlds, the rise of life, the growth of thought, flows naturally toward calm. Entropy, often described as decay, is also the mechanism of rest. It allows energy to find its most even distribution, its quietest state. In that balance lies beauty, nothing wasted, nothing lost, everything continuing in a gentler form. Sleep is your nightly rehearsal of that truth, a brief return to balance after the bright activity of waking hours. Imagine now that you are part of that vast night, floating within its quiet expanse. Around you, galaxies fade into distance, their light stretching into infinity. The air grows still, thought becomes soft. You can feel gravity's gentle hold, the earth turning slowly beneath you, the hum of motion continuing while you rest. The same laws that keep planets in orbit cradle you now, drawing you towards stillness without effort. Let your breath follow the rhythm of the universe, steady, expansive, calm. Inhale as if gathering the light of stars, exhale as if releasing it back to space. The night sky above and the stillness within are not separate. They are part of one continuum, one gentle process of balance repeating on every scale. You are part of that process, as natural, as enduring, as necessary as the cosmos itself. When you close your eyes, the light that traveled across time continues its journey, and so does thought. The universe does not end when you sleep. It continues quietly, holding you within its pattern of rest and renewal. And when the next dawn arrives, it will be another beginning, just one more moment in the endless flow of matter, energy, and awareness. For now, the night is enough. The silence of the stars and the calm of your breath are one and the same, both reminders that peace is not separate from existence. We, from Sleepy Stories, wish you a good night.